Good morning, mathematicians. Oh, there we go. Okay. How's it going? Guess it's time to dive into Tate's theorem. Pretend we fully understood the proof of the previous situation. I'm surprised no one follows the series has corrected me yet, or not corrected me, but pointed out the proof. Pretend we fully understood the proof of the previous situation. But maybe if we push ahead, things will make sense. I'm tired. I didn't have an amazing sleep last night, so we'll see how the old noggin is firing. And look at this, remembering to put top chat to live chat like every time now at the start of stream. Like I said, I'm the best to ever do it, clearly. Okay. Tate's theorem says that if G is a finite group and C is a G module, and if we suppose that for all groups, made you want to go back to understanding Tate's theorem better, and you think you have a good intuition for it now. Nice. And do share. Aren't you supposed to be restarting your blog and telling us about that too? So get on it, man. Highly recommend the last two sections of Tia Wall's chapter in Castle's Froelich. Oh, okay. Did they prove Tate's theorem there? Supposed is carrying a lot of weight. Yeah. Well, get on it. Where are we? Tia Wall. Okay. Tate's theorem. Oh, but it's only telling me. Oh, okay. It should be page 113. Okay. Let's see. Nice. We were pretty close there. Have ourselves a little look-see. Like theorem 8. No. This sort of looks like... Okay, Tate's theorem. Here we go. Finite group. Let this be CLP subgroup. Well, this is phrased a little differently. I guess it's equivalent. I'll be honest, purely for the fact that I don't love the typesetting. I'm going to go back to Milne for a moment, and maybe I'll go back to that. I think I have a copy of Castle's Froelich, a hard copy, in the office. But I can't deal with the typesetting, I'm sorry. Theorem becomes quite well motivated if you start by generally studying Galois cohomology of FP vector spaces. Okay. Let's look at the statement here. G is a finite group. C is a G module. And we suppose that for all subgroups, including the big one, that H1 is trivial and that the second cohomology is cyclic of this order. Yeah, I mean, this does seem highly unmotivated, but the fact that you said that makes me think, okay, well, will end up being useful. Then for all R, there is an isomorphism. Oh, okay, interesting. Okay, so choose a generator in here because of this composition. The restriction generates this for any subgroup H of G. Okay. Okay, I can believe it. Right, okay, so we have one generator. Am I learning? I'm trying. I'm trying. So I guess we just want to show that this, now we have a generator, we have a single generator, and I guess we just want to show that this generator has infinite order, right? Good morning, Ken. This proof is a bit different, but for what it's worth, you should think of C phi as the mapping cone, slash homotopy cofiber in the derived category. So you're detecting isomorphisms by vanishing of the homotopy cofiber. Let's see if I can make sense of that. Oh, I see. Right, because we are defining this to be a direct sum. I can kind of see only 75% is true. Okay. But I can, okay, yeah. Yeah, because I'm thinking about in like the abelian category, like the derived category of the abelian categories, we do build the mapping cone out of this direct sum. Yeah. So I could believe it. I'm so tired, Ken. I don't know if I said good morning in response to your good morning yet. Okay, C phi is a direct sum of C with the free abelian group having symbols for G, for the non-trivial elements of G, and extend the action of G on C to an action here by setting this. Good Lord. Okay, but here's the confusing thing. Would this not end up creating the identity element somewhere? So it says you have a basis one for each non-identity element. But if you took sigma to be tau inverse, then wouldn't you have the basis? Oh, here we go. This is why you got to keep reading. This is actually a good learning point. There's been a number of times where I've talked to students and, they do, where did I go? What did I click? Where they will read something here and they'll stop at this period and then they'll be horribly confused. And then they'll come to me and they'll be like, I'm confused. I don't know what they mean. And I'm like, did you read the next sentence? So sometimes reading ahead helps. Okay. This does define an action of G on here because reasons. Because those... Sure, okay, whatever. That's just algebra. Whatever. And it agrees because phi satisfies a co-cycle condition. Okay, that's fine. That's just algebra. Note that phi is the co-boundary of the one cochain. Right, because this is G into this module. Sure, okay. Okay, again, I guess we could just see that by doing the algebra. So so gamma maps to 0. Okay, hang on. Gamma is a generator for H2. Gamma is a generator for H2. Phi is a co-cycle representing gamma. Oh, right. It's a... Okay. Yes. Okay. Right. Because phi represents gamma, and we see that it is the co-boundary of a one cochain. Okay. So, for this reason, I don't understand why this is the reason, but C phi is called the splitting module for gamma. That I don't understand. That I don't understand. That I don't understand. Why is that called the splitting module? Because it splits? Gamma ends up in one component of it? Yeah, I don't totally get that, but okay, whatever. It's just in a name. C phi is exactly meant to kill the cohomology class of gamma. Okay. Why would we call it splitting then, though? I don't know. So it makes the extension represented by gamma a split extension. Oh, right, because gamma's in H2, so we have an extension. I see. Thank you, Arad. That makes sense. Okay, so then we are going to claim that these should follow from the hypotheses of this theorem for all subgroups. So we have our augmentation sequence. Is that what you would call it? I guess. Because ZG is induced, this is trivial, and so we get these isomorphisms. Right. That's just definition. And then why do we have that this is 0? I'm good with the first isomorphism, but H1 of HZ, this I'm not so clear on. Did we have some general theorem about this? Why is H1Z equal to 0? Isn't that one of the assumptions? Oh, yes, it is. Thanks, Arad. Hey, Thomas, how's it going? Okay, so then we define a map, alpha, but we just call it an additive map. We don't call it a module map, which is interesting. Clearly this is an exact sequence of G modules. Okay. Its cohomology sequence reads as such. Why is that the zero map? The zeros at the end use that H1C is 0 and this is 0. Reading up for your undergrad thesis. Nice. Nice. Hope it's going well. The zeros at the end use that this and this. No, that's not making sense to me. The map here is 0. Because H2HC is generated by restriction. He's explaining the 0 at the end here. Okay. Because this is generated by restriction, and this maps to the restriction of the image of gamma in here, which is 0. Okay. Actually, that makes sense. Okay, I'm happy with that. I don't know about you guys. Therefore, H1 HIG into here is on 2. And hence is an isomorphism because the two groups have the same order. When did we compute the order of these groups? Huh? When did we compute the order of these groups? Yeah, I'm sorry. I don't think. When did we compute the order of this? Is this supposed to be an obvious way to compute it? Okay, actually, I guess it's reasonable to say that based on the definitions we have of the cohomology groups. In these cases, we have explicit definitions. And, we're just computing the order of some groups. So actually, okay, I'm willing to believe it. This is definitely a theorem. I'll need to go back and read the proof to myself again someday. We deduce from theorem 3.10 that this is 0 for all R. Let's go back to that theorem. Theorem 3.10. Oh, that was the one right before. If H1, H2 are 0, then that. Okay. Unsplicing the two short exact sequences together. What does that mean? What does that mean? I guess you just... Right, because there's an IG in both of them. Okay. We get this with the property of these things for all R. Therefore, the double boundary map. What is the double boundary map? Consider an exact sequence, a short exact sequence. Then the cohomology sequence becomes this. and the collection of isomorphisms here. Yeah, but this has 4 terms. Well, I don't know. Maybe we should turn our attention to some other books. I'm not quite ready to give up on Milne, and there's these interesting applications coming next. Okay, let's read these follow-ups, and maybe I'll have to do some, I don't know, research to see if I want to switch books yet again at this juncture. Yeah, I don't know. Let's read the remarks, and then we'll finish it up there for today. Okay, so if we have a G module where Tor is trivial, if either M or C is, Tor 1Z, this just means as abelian groups. Well, that tracks with saying in the case when M or C are torsion-free as Z modules. Then one can tensor the above 4-term sequence and obtain some isomorphisms here. It's going to be a good math book when the text is slanted and you can't highlight anything. You mean here? Yeah. That's how you know you got that good. Yeah, I don't know. There's just something about the font. There's just something about the font I don't like. But maybe I will go take a look at this. Take a look at their exposition from the beginning. We'll see. Okay, so he's just highlighting some random isomorphisms we get. Okay. The map here is cup product with the chosen element gamma. Okay. Now here we get into some number theory. If K is a local field, we shall prove that for any finite Galois extension L of K with Galois group G, H2 on L cross, the video is skipping every once in a while? Oh. That's weird. I don't know what to do about that. In a TIA wall, just the last 2 sections should be great for what I already know. Okay. But then again, I just feel like, Arad, having just looked at it there, I don't know, there's a part, it's just the way that my brain works. There's a part of me that feels like I need to go back to the beginning to see how they're doing things, if that makes sense. You know what I mean? It's like, I feel like I need to follow their train of thought from the start, but... That's just me. So we're going to show that this is a cyclic group of this order with a canonical generator. Ooh, what does canonical mean here, gang? Yeah. Our most specialist boy, ULK. Since we know from Hilbert 90 that H1 is 0, Tate's theorem shows the cup product with this is an isomorphism, specifically from the abelianization of ht minus 2gz to ht0, which is k cross mod the norm. Canonical means compatible between different extensions. Oh, okay. So it's not that we chose a single most specialist boy. Or maybe it does mean that. And that most specialist boy is compatible between different extensions. So surely there should be a way to dress this up in a functorial way, or to write it as a natural transformation of sorts, maybe. And the inverse of this isomorphism is the so-called local Artin map. Very cool. Well, that might be a nice place for us to leave it here. Leave it off here. Nice little application. I mean, I would really like to see this bad boy in action, I guess, when we get to some local class field theory, and say something about the classification of extensions, abelian extensions or something. But I don't know. So I might have to do some searching to see what where we go next in the series. So those of you most devout followers, let me know in the comments, because I mean I am interested to think about cohomology of profinite groups, and definitely we're going to need that if we're going to do infinite Galois theory. But let me think. So what would be after this? I mean, we could stick with Milne and jump into local class field theory, which would then allow us to put all of this, all of these theorems to work. I think that's most likely what we're going to do. But yeah. I think that is where we're going to leave it for today, though. So thanks everyone for joining me.